Alright, let's begin this video lecture. This video lecture will feature an overview of something called volumetric analysis. Volumetric analysis. This is also associated with this titration process. It's pretty important that you master this concept and you understand what this is all about. I'm probably going to rate it 3.5 out of 4 stars here. Importance. You're likely to see semester exams that cover titrations. You'll see this in the lab for sure. And if you take an end of the semester standardized exam, you're probably going to have questions that are dealing with titrations in some way, shape, or form. So it's important that we understand what that question's talking about and some issues related to this volumetric analysis. Okay. So basically the way that this volumetric analysis works, it's a way to measure analyte in a sample. The volume of a known reagent that's required for complete reaction with the analyte by a known reaction is measured. This first statement is sometimes assumed, but it really shouldn't be overlooked. Okay, what we're going to do in a volumetric analysis is add a known amount of a chemical reagent that reacts or neutralizes an analyte completely. And for that to happen, the reaction has to be known. It has to follow a known stoichiometry. That is the ratio in which these chemicals combine to react. It has to be known. And it also has to be stoichiometric or proceed to completion. Okay? If the reaction doesn't proceed to completion, boy, all bets are off and we're in a world of trouble. So we can only use reactions that essentially proceed to completion, that are known and have a known stoichiometry. And that's important, okay? You cannot overlook that. Oftentimes these experiments are set up such that that's already built into the experiment. But if it's not, and you're developing some kind of new volumetric analysis, that would definitely be a requirement, okay? Must have complete stoichiometric reaction, or else you're in a bit of trouble. Usually, or often, this volumetric analysis is carried out by a process referred to as a titration, okay? If you've been around chemistry classes very long, you have seen titrations because they're very popular to carry out in the lab. And there's a couple reasons for that. I mean, one, it demonstrates the quantitative nature of the work, and generally speaking, these reactions are relatively low cost to pull off in the lab, the instructional laboratory. So it makes it sort of friendly for your university or your high school instructor to do titration reactions and show you a little bit about quantitative chemistry if they don't have resources to talk about other methods. But what a titration reaction really looks like in the laboratory, or how it proceeds, is you put a solution into a long cylindrical glass tube called a burette. Okay, so you use a burette, a long cylindrical glass tube. It's oftentimes 50 or 100 milliliters in volume. Just these little graduations on the side to tell you what the volume is, okay? The solution that you put in there is called the titrant. Okay, the key word for this section of the class. So what we're going to do is we're going to use the burette to deliver the titrant into this receiving flask. Okay? Now I use that word to deliver, right? Burettes are going to be calibrated TD, that stands for to deliver, so they're going to deliver the stated volume into a receiving flask. And the way the experiment works is we basically keep delivering titrant into this receiving flask until we reach the end point of our titration. Now the end point is usually signaled by some color change in this solution, or some other physically sensible phenomenon that occurs. Okay, maybe it's using a pH electrode or something like that. We see a huge pH change, but there's either a color change or some sort of physical chemical change in this beaker that occurs that we can monitor either using a device or just visually. Okay, and when that endpoint occurs, we stop the titration. We note how much volume of titrant was delivered. So we figure out how many milliliters of titrant was delivered, and that's important. It's one of the measurable variables for the experiment. And the reason why is because the solution that we put in here as our titrant, it's usually a standard solution, or it has been standardized. And of course what that means is that titrant solution that we put inside that burette, the concentration of that solution is known to a high degree of certainty. We know the molarity, we know the concentration of this solution. So if we know the molarity of the solution, and we know the volume that we dispense, we can use a very, very friendly equation. That the molarity times the volume in liters is equal to number of moles. So if I know my molarity of the titrant, if I know the volume dispensed, I can compute the moles of titrant that were dispensed. And the beauty of that is if my reaction between the titrant and my analyte, which is down here in the beaker, if the reaction between the analyte and the titrant is stoichiometric and quantitative, and I know the stoichiometry, if I know how many moles of titrant were required to react with the analyte placed in this beaker, I can then, through some mathematics, figure out how much analyte was present in this beaker. And that's the whole basis behind titrations, more or less always. Okay? That's what you do in a titration. You meter the titrant, figure out how many moles you added, and then through the reaction stoichiometry, figure out how much analyte must have been present in this beaker or flask to react with your titrant. That's a titration in a nutshell. Now, how do we determine when the reaction is complete and all of our analyte is used? That's an important step in a titration. Okay? This is how do we detect the end point of the titration? Well, we can detect a change in voltage or current between electrodes, perhaps. If you have a pH meter in the lab that you use, you're really sensing a change in voltage on the probe that's placed in the solution. That's one way you can detect the endpoint. A more familiar way, perhaps, or common, just because it's a little bit lower cost, is use of an indicator compound to detect the color change. An indicator is a substance that's got a physical property, and almost always it's the color, that changes when the analyte is used up. Now, that last sentence, I don't necessarily like the phrasing of it, that when the analyte is used up. That's probably not technically correct. Usually what happens is there's a pH change inside this beaker. If you're doing like an acid-base titration, there could be a pH change inside this beaker, and that could lead to the color change. Okay, but that pH change is somehow linked to using up the analyte. And when you talk about computing the pH along titration curves, it'll make more sense why that is. Okay, but a color change can be used to signal the endpoint of our titration. If we have an instrumental detector, some sort of spectrophotometer, we may be able to measure the absorbance of light by a species in solution. And if that absorbance changes at a particular wavelength, that's kind of synonymous with the color change or the light absorption change. Okay, so those are some ways we can find the endpoint of a titration. There's some graphical methods that we'll learn about in a bit as well. Now, you may have seen some reactions based in titrations already. For instance, if you've ever gone into the lab and did an acid-base titration, there's a reasonable chance that you titrated hydrochloric acid aqueous solution with sodium hydroxide aqueous solution. Of course, a product of any acid-base reaction is water and some salt. Here it's sodium chloride. Okay, so this would be an example of a very simple acid-base titration that you may have seen in the laboratory already. Okay, another example that you may encounter in the lab course or a lab course, something like this. This is actually a redox titration. It's not acid-base. It's really a redox titration, oxidation reduction reaction that occurs in the titration system. There's many different categories or types of titrations. This is acid-base, this is redox. There's complexiometric titrations that you'll learn about in the course as well. So there's different classes or categories, okay? But they always kind of tend to proceed via this tetrametric setup. Now, in this particular redox reaction, you see what we've got is this substance, which is oxalic acid, and it'll actually react with permanganate ion in aqueous solution that's been acidified. Okay, so we're going to make our sample matrix in this beaker a bit acidic, and usually you add some acid to do that. Okay, but in such a solution, the permanganate ion will react with the oxalic acid to make carbon dioxide, water, and manganese 2+. So we can see our manganese here has been reduced and this guy's been oxidized as a result of this reaction. Okay, so it's a redox reaction. The cool thing about this reaction is we might call this one our analyte here, and this one be our titrant. So we'll put the permanganate here in our burette. If we run the reaction in this way, this substance can actually serve as its own indicator. We don't have to add a third substance. And the reason why that is because if you've ever seen a permanganate ion in solution, it's kind of a nice, sort of pretty dark purple or light pink color if you really dilute it. Okay. So this burette will be full of this, purple colored solution, deeply purpled. That's how it would generally appear in this burette. However, and when you titrate it, okay, and it reacts, that color is basically destroyed, okay, because these guys obviously don't have any color, and this manganese 2+, at best, it's a very, very faint yellow color in solution, but it's very, very faintly colored. So the color basically disappears in the products. There's no colored products over here. So while you're mixing these guys and they're reacting stoichiometrically, there's no color in the beaker. There's basically clear and colorless. However, as soon as you run out of your analyte, the oxalic acid, and you add 1 drop more of the permanganate, well, there's nothing for it to react with anymore. And that 1 drop will impart a pink color to that solution. So you actually keep titrating until a pink color results. And at that point, you know that you've reached the end point and you should stop titrating and work your mathematics, okay? That's kind of an interesting example. This reaction is also interesting as well because it's actually an example of an autocatalytic reaction. If you do this in lab, it's actually catalyzed by this product. So it'll speed up as the reaction proceeds. It'll seem like it takes forever at first, but it actually speeds up as the reaction proceeds, which is kind of interesting, actually, as it turns out, to watch visually if you ever do this experiment. So a bit more terminology at the bottom here, which is important. When you're talking about titration, some vocabulary comes up. Endpoint and equivalence point. Turns out these two things are not the same. They're not the same, okay? The end point is when the color changes in the titration, where you usually stop the titration, you get the color change. That's the end point of the experiment in the lab. The equivalence point is when the reactants come into stoichiometric equivalence. In other words, the equivalence point is that point in the titration where I've perfectly added, or I've added the perfect quantity of my titrant to react exactly with my analyte in my beaker. So I've added just enough of my titrant to neutralize my analyte that's in my beaker. That's my equivalence point. So it's a theoretical thing, okay? Experimentally, we observe the end point where the color changes, but the equivalence point is where they're in stoichiometric equivalence. Okay, so they're not the same. Now, if you think about this long enough, it doesn't take long to realize that, well, you certainly hope that your experimentally observed endpoint is exactly the same as your equivalence point, right? I mean, you want the color to change right when this happens. Because if that's not the case, if it changes color at a different point besides when you're in equivalence, guess what? You're going to have titration error. If your color changes after 1 drop, but not all of your analytes neutralized, boy, you're in big trouble, right? Your titration's not going to say anything about how much analyte's present in your beaker. You'd have a huge titration error. Usually we design our titrations to minimize the titration error. We design them such that the endpoint is very, very close to the equivalence point. But please realize that they're always a little bit different, okay? There's always going to be a little bit error. Remember this example I gave you a second ago where we were titrating our oxalic acid with the permanganate, and I said we kept titrating until it got a little bit pink in this beaker? Well, that pinkness was imparted by an extra amount or extra drop of the permanganate. Now, if we're really good at this experiment, maybe that's an extra half a drop or 1 drop or something like that, okay? But you can see that we had to add a little bit extra of our titrant to make the color change. Well, the difference between what we added and what we needed to add to completely neutralize this would be our titration error. So typically they're not the same. In a well-designed experiment, we can minimize the titration error or minimize the difference between the two, but they're generally not exactly the same. Now, another important concept that comes up when you're talking about titrations is going to be the standardization of solutions. This turns out to be a pretty important topic, okay? Now, I didn't really allude to this much on that introductory slide. I just said that, oh, you make a solution of the titrant and you put it into the burette. Well, before you put that titrant into the burette to do your analysis, you have to be really confident that the solution that you're putting into that burette is a known concentration. Okay? So your titrant must be known concentration. That's important. If it's not a known concentration, how can you determine the analyte? Through volumetric analysis. So we have to think a little bit about how we can achieve knowledge of the concentration of the titrant. And there's really two different ways that you can do this, okay? And one is to use a primary standard directly. And the other one is to standardize a solution using a primary standard, okay? So both of these, whichever option you take, comes back to using these primary standards. So let's talk about what that is first, okay? A primary standard for an analysis is going to be a reagent that is used to standardize a solution or measure its concentration. A primary standard should be available in high purity. That's very important. Not decompose under storage conditions. Be stable when dried or heated. Have a high molar mass and have no waters of hydration. These are characteristics of primary standards. The reason why this is important is because a primary standard is the chemical that you're going to go into lab, get off the shelf, and weigh out some onto a balance. And when you do so, that mass that you record of that standard is going to serve as the primary reference, if you will, or the primary basis for the accuracy of the entire analysis subsequent to that. So you've got an unknown in a beaker. You want to know the concentration, okay, and maybe you know this unknown analyte reacts with a primary standard. So you're going to react that primary standard with this. You're going to do a titration. But the problem is if that primary standard that you use is not pure, if it's got contaminants, if it decomposes, which essentially leads to impurities, okay? If you use that chemical for your analysis, you may weigh out 1 gram of it for the analysis, but do you really have a gram or do you have less than a gram because of impurities and such, okay? So this primary standard is the chemical that serves as the basis for your analysis. And because of that, it's extremely important that it's available in high purity. Because if it's not, if you weigh out a gram, do you really have a gram? Or do you have half a gram, right? So, got to be greater than 99.9% pure. We don't want it to be decomposing. We want it to be stable when dried or heated, because oftentimes, of course, what you do with these is you'll dry them in an oven to drive off water, say, for instance, that might accumulate in the substance if it's hygroscopic, right, which just means that it absorbs water well. So hygroscopic means it absorbs water well from the surroundings. And to get rid of the water, you just dry it in an oven, maybe 110 degrees for overnight or something like that, and then store it in a desiccator, a dry desiccator after that. So if you can't achieve a primary standard, or you don't have a primary standard, you're in a bit of trouble. All right? So usually when we're working in lab, we'd like to use these primary standards. Now, there's another problem. Not every substance fits all of these conditions. Like, for instance, sodium hydroxide. We use that in lab all the time for titrations. It's not considered a primary standard. There's a couple reasons. It's difficult to obtain in high enough purity, And in addition to that, particularly in humid environments, it's very hygroscopic and it'll absorb water from the surroundings. It also reacts with carbon dioxide in the air, which is also a bad thing for its potential use as a primary standard. So it's not a primary standard. So if we want to use sodium hydroxide in our experiment, what we need to do is make a solution of the sodium hydroxide. So we can add some pellets in there, get it to the approximate concentration that we want. And then after we make that solution, we have to standardize it. Or we have to undergo the process of standardization. What standardization is a titration experiment, a separate titration experiment that's done before the analysis, that is done to determine the exact concentration of the titrant. So what that means is I may take some of this sodium hydroxide that I've prepared, put it in my burette, and run a titration against a primary standard. And in doing that, I can solve for the concentration of the sodium hydroxide. That's standardization. It's running a titration experiment with the sole purpose of figuring out the concentration of the solution you're going to use for your titrant. Standardization. The result of this process is coming up with a standard solution. This is a solution whose concentration is known to a high degree of certainty. Okay? So if you have a primary standard that you can use in the analysis directly, that's wonderful. Okay? By all means do that. If you do not have a primary standard available to you in your laboratory, or else one is just not available through purchase, what you typically need to do is standardization. And whenever you use sodium hydroxide solutions in lab, you have to standardize them first, because it's not a primary standard. It's just not. Okay? Now, it would be kind of useful for you if you developed a toolbox or toolkit of some common primary standards that are used in analytical chemistry. And the one that's shown down here is called KHP. KHP is sort of the prototypical example of a weak monoprotic acid primary standard. So it serves the reaction function of being a weak monoprotic acid, and it's a primary standard. Now, sometimes students get confused about this formula KHP and they think it's potassium, hydrogen, phosphorus, but that is not correct, okay? The full name is potassium hydrogen phthalate, is the basis for the P, and it has no phosphorus whatsoever. It's an organic molecule that looks like this. It's got the 6-member ring with the carboxylic acid group here. That one's protonated. That's our monoprotic acid functionality. And this other acid group down here, the H plus has been replaced with a K plus, okay? If this was an H plus, it would be phthalic acid, which is a diprotic acid, but in KHP, one of the two H's has been replaced. So it's a monoprotic acid. So it turns out we're able to buy this from chemical suppliers in high enough purity that it can be a primary standard. You can dry it overnight if you want to and store it in a desiccator to keep it dry. Not a big deal. It's got a pretty high molecular weight as well, which is also a good thing for us. Okay? And the reason why that is because when you convert to moles, like if you waste some of the KHP out and you convert it to moles, the higher this is, the less relative uncertainty in the result, basically. Okay, so that's why we like to have the high molar mass. So KHP will react with sodium hydroxide in a 1-to-1 stoichiometry. And what happens there, of course, is the Na plus and the H plus sort of about to switch places, if you will, okay? And of course, in any acid-based chemistry, we got to make our water, okay? The 1-to-1 stoichiometry. So KHP, you'll see this in lab if you take lab. It's really the prototypical weak monoprotic acid primary standard. If you ever need to standardize sodium hydroxide, very often that's done through titration with KHP. And the way the experiment would work, you just weigh out some of this, maybe 0.5 gram to 1 gram, put it in the bottom of a flask, add some water, some indicator, oftentimes phenolphthalein is used, and then you just titrate with your sodium hydroxide until you see the color change, and you could figure out the concentration of your titrant through this process because you know how many moles of this you added to the container. So KHP is a very, very commonly used monoprotic weak acid primary standard. Now, you say, okay, well, KHP for an acid standard, what about for a primary standard base that I might use? Probably a pretty good example for you to keep in mind for a base would be sodium carbonate. It's commonly used when we need to have a base as our primary standard. Sodium hydroxide, remember, will not work, okay? If you're thinking about redox chemistry, a good example for a primary oxidizing agent, K2CR207. Which is potassium dichromate. It's a commonly used primary oxidizing agent. So this tutorial basically just went over the basics of volumetric analysis, oftentimes referred to as titrations. We talked about primary standards. We talked about some requirements for primary standards. And I hope that this has improved your understanding of the volumetric analysis through titration. And we shall see you in the next video.